Let's start about the curvilinear coordinates. Firstly, we know that in case of a Cartesian coordinate system, if we take this axis as x axis, this is y axis and this is z axis. So this plane is the xy plane and this plane is called as z equals to 0 plane also. Now if we shift upwards along z direction and draw another parallel plane of the xy plane, that is z equals to 0 plane, we get z equals to c here, where c is a constant. It may be 4, 6, 2, 8, any number. How much amount we proceed along z axis, we get z equals to that number according to the displacement along z axis. And any point in this coordinate system is written as x, y, z. This is the Cartesian system representation. Similarly, we can say that x equals to a constant c1, which gives a parallel plane of yz plane. Similarly, y equals to c2 gives the parallel plane of xz plane. And already we have seen that z equals to c3 is a parallel plane of xy plane. So now we shift our discussion to an arbitrary system of coordinates. Let we take the system of coordinates as u1 equals to c1, u2 equals to c2, u3 equals to c3. So just like this set of equations, we get that x equals to c1 and y equals to c2 when intersects. When the intersection will be found of these two planes, it will be surely the z-axis. Similarly, here also the two pairs of equation intersect, two pairs of surface intersect to give the third one. This is the position x, y, z. So here it will be u1, u2 and u3 in our arbitrary system of coordinate. Now, in the Cartesian coordinate system, the position vector of a particle is x I cap, y z j cap and z k cap. And where I cap is equal to del r by del x whole divided by mod of del r by del x. This is a very simple procedure to find the basis vectors I hat, j hat and k hat of the Cartesian coordinate system. Similarly, j hat is equals to del r by del y divided by mod of del r by del y, and k cap is equals to del r by del z divided by mod of del r by del z. So in general, if we take that like r as a function of x, y and z, here we take the r as a function of u1, u2 and u3 in our new coordinate system, which we have taken arbitrary. So With the similarity of these expressions, we can take that the unit vectors of this system, the basis vectors of this system will be taken as E1 hat is del R by del U1 by mod of del R by del U1. As here U1 is written in place of X. So if I cap is given in such way, similarly E1 cap is written in such way. So E2 hat also del R by del U2 by mod of del R by del U2, and E3 cap is equals to del R by del U3 by mod of del R by del U3. These three equations are written in such way. And we can take these three axes in such a way that this is E1 cap, this is E2 cap, and this is E3 cap. But the curves are as such that the E1, E2 and E3 are the tangents to the curves. We can take this is E1 cap, so the tangential unit vector is E1 cap. Here it is U2 curve, so the tangential unit vector is E2 hat, and this is U3 curve, but the tangential unit vector is E3 hat. But the concept is very similar to the Cartesian system of coordinates. Now, this mod of del R by del U1 is written as H1, that is del R by del U1 by H1 equals to U1 cap. So we can write that del R by del U1 equals to H1 U1 cap. Del R by del U2 is similarly written as H2 E2 cap, and del R by del U3 is written as H3 E3 cap. These H1, H2 and H3 are called the scale factors. In the orthogonal curvilinear coordinate system, we write E1 hat in place of I hat. So as I hat is perpendicular to J hat, so I dot J is 0. Here also E1 dot E2 is 0. All the pairs are written in such a way J dot K equals to 0, K dot I equals to 0. So here also E2 dot E3 equals to 0, E3 dot E1 is also equal to 0. So these E1, E2 and E3 make a orthogonal curvilinear coordinate system. Now, if we shift ourselves to the cylindrical coordinate system having a position of a point R, that is function of rho, phi and z. This is the xy plane and this is the z axis. So we can take the cylinder in such a way so the axis of the cylinder coincides with the z axis of the Cartesian system. The radial direction, the radius is rho for the cylinder. and a point on the circular cross section taken from its own axis, and the foot of the perpendicular goes to the xy plane or the base plane, and then the line from the origin makes an angle with the x-axis, that is the angle phi. So these are the descriptions of x, y and z and related with rho, phi and z. And here, as it is a circle, the cross section is circular, so obviously we can write x equals to rho cos phi, y equals to rho sin phi, and as z coincides with the Cartesian z, so z equals to z here. So we can write r vector equals to rho cos phi written with I hat plus rho sin phi written with j hat plus z k hat. This is the r vector written in the cylindrical system. So the basis vectors will be E rho. We have already learned that del r by del rho divided by del r by del rho mod gives the E rho. So here it will be I hat cos phi plus j hat sin phi, and the mod value of this is 1. So the h1 is equals to 1. Here h rho equals to 1. Similarly, you can find the E phi and Ez. The E phi hat will be j cos phi minus I hat sin phi. Here a rho is will multiplied and the h phi is also rho. So in this way we can find the E rho, E phi and Ez will be simply k hat. So if we now make a dot product with each of the pairs of the basis vectors, we get 0 result for each pair. So the cylindrical coordinate system is orthogonal curvilinear system.